Say there was a factory where there is a reactant called A and B, and it goes into a machinery and it produces C and D as the product. Something like this would be related to chemistry in that you have two chemicals together and then you generate a two product in the end. Say another example would be where now you take the product, which is the C and D, and then it goes into machinery, and then output is A and B. So it has ability to do a reverse reaction. But this factory is interesting because this factory has, at one point in time, they're going to produce the product, the C and D, and then now the product is going to then reform into A and B. There is a reversible. Notice that in all of these three scenarios, there is a little symbol on the top. On that top, this one says KC, the other one says QC, and this one, the very beginning, says QC. The QC represents reaction quotient, whereas the KC represents equilibrium constant. And we will go over more in details in relation to chemistry in a moment. So now is a good time to introduce that vocabulary word, equilibrium constant. Equilibrium constant measures the relative amounts of the product and reactant at equilibrium. In other words, we can describe this as if there was A and B as a reactant forming into C and D, as we have seen in the example previously regarding that factory. Well, that C and D can reform into A and B, and it's happening at the same time. In fact, at the same rate. Imagine that this A, B, and C, and D are chemicals that are in real life, okay? And those particular A, B, C, D are gas or aqueous. And also the number or the letter that is in front of the A, B, C, D represents the coefficient in the balance equation. So whether it's 2 or 3. And we can put these in the equilibrium constant or the Kc. Equilibrium constant takes the product in concentration with exponents in the top. The exponent represents the coefficient that's in the balance equation, and it's all over the reactant concentration with the coefficient in the front. So therefore, now we can see that the concentration of A and B and C and D, these are all expressed in molarity, also known as moles over liter, or that big M. And the exponents, again, are the equilibrium or the balance equation coefficient. Now, the K concentration must be at equilibrium. It can't be any other point in time. It can't be in the beginning of the reaction, or it can't be in the smack in the middle, but it tends to be when it has reached equilibrium. If it's in any other point than the equilibrium, then we are trying to look at the reaction quotient, which is Q. And so Q is equal to the same thing as Kc. It's just that the values of the CD and the AB will differ. Let's take this example to express equilibrium constant even further. So here you see that SO2 and oxygen gas is forming into SO3. The reaction quotient for this expression is as follows. QC is equal to the concentration of SO3 to the second power and SO2 to the second power, and these second powers are coming from the coefficient, and oxygen, and we write to the first power, or we don't even need to write 1, but we know that there is an imaginary 1 in front of the balance equation. What about equilibrium constant expression, or Kc? It's going to be the same thing. The second power, SO2 to the second power, and oxygen. So you see how both of the equation are exactly the same. It's just that you write Q in the front, the other one happens to be K. Now, of course, the values are going to be much drastically different. If we're looking at the beginning of the reaction, say there is no product and there's plenty of reactant, as time passes, you'll see that it starts to diminish. The reactant starts to diminish as the product is being formed, and that makes sense. Now, all of the portion over here, this, if you want to find the reaction quotient expression, we are going to express it in QC. But after this point, after equilibrium has reached, unless there is an external source that changes that equilibrium, it's going to be constantly Kc. And it doesn't really matter. This value where in which the QC from, say, you only have the product, you only have SO3, and as time passes, that starts to diminish, whereas reactant is being formed. Well, you're going to reach a certain point, and that's going to be Kc. The value, whether you go from the forward or you're coming from the reverse direction, you're going to end up with the same reaction, same value of the Kc. Again, that goes with that law of mass action. At a given temperature, the reaction quotient for a system at equilibrium is constant, meaning that the value of the Kc, whether it's coming forward direction or the reverse direction, you're going to reach the equilibrium, and that equilibrium value is going to be the same. All right, let's do a learning check based on what we have learned so far. So here it says gaseous nitrogen dioxide forms into dinitrogen tetroxide according to this equation. When 0.1 mole of NO2 is added to 1 liter flask at 25 Celsius, the concentration changes, equilibrium, and then it gives you the concentration of the nitric dioxide and also the dinitrogen tetroxide. And at A, it says, what is the value of the reaction quotient before any reaction occurs? Okay, so before it even hits the equilibrium. So here's A. We know that QC is equal to the product, which shows N2O4, and it's to the first power. And you have the reactant, which is to the second power, right? Now, before any reaction occurs, this is my product over here. Do I have any product? No, it doesn't show this. It doesn't say that there is any product here in the very beginning. You just have this. So what does that mean? That there is nothing here. It's going to be the value of 0. So we don't even need to know the value of the bottom, because anything denominator or numerator that is 0, we're going to end up with a QC of 0. So reaction quotient would be 0. B, it says, what is the value of the equilibrium constant for the reaction? Now we're asking for Kc. So Kc is the same thing. And it tells you what the value of the concentration at that particular point, which is the equilibrium point. So I'm going to just go ahead and plug those in for 2. And this would be 0.016 to the second power. So we're going to have to calculate this out. So let's go ahead and take out our calculator. 0.042 divided by parentheses 0.016 to the second power. And then I'm going to close it. Enter. So I have 164. Okay, 164, and I'm going to go ahead and put this into 160 with the correct sig figs, since there's 2 right there, 2 sig figs. So 160 would be the equilibrium constant for this particular reaction. So 160 is a rather pretty large equilibrium constant, and having this large or small equilibrium constant, we can start to interpret them, and let's go ahead and interpret them in the next slide. Here it shows that the reaction quotient or equilibrium constant, I apologize, if it hits very, very large, so if Kc is large, that means my product was probably really large. Having that numerator large, it makes the reaction, the equilibrium quotient or equilibrium constant really big. So therefore, most of the reactant then has formed into a product at equilibrium. But say you have a very small K value, small equilibrium constant value. What does that mean? That means very little reactant has converted into product, meaning, so here's this one was large, meaning that you have a very large value of the reactant. So not much product has been formed. Just because you have a lot of reactant does not necessarily mean you're going to get a lot of product in the end, because the equilibrium constant does not allow that. So, but also you need to know that equilibrium constant K, it does not mean that the reaction is going fast, okay? Just because a reaction value is 160 does not mean it went fast. It just means that there's a tendency to form into a product more than the reactant, but it doesn't determine the reaction rate. Just keep that in mind. Here is another way for me to interpret what K means. So here you see a carbon monoxide and water forming into carbon dioxide and hydrogen. I'm going to go ahead and explain before and at equilibrium in a moment. So let's look at the before. Before, you have in the very first mixture, in the very beginning, you have just carbon monoxide. So you have carbon monoxide here, and then you have water. There's no product, so that's why you see the reaction quotient being 0. Oh, let's go ahead and write the reaction quotient for this. So reaction quotient to help you out is CO2, H2, carbon monoxide, and H2O. So in this mixture one scenario, we don't have any product, so hence why it's 0. Now, in mixture 2, you just have only the product. So you only have product. You have product, but none here. If you have a 0 on the denominator, we consider this having Q is going into infinity. Here at this point at mixture 3, you'll notice that there are some reactants, okay, but there's also some little bit of product in the very beginning. Now, as time passes, these are all going to reach equilibrium. You see this value, but you see 0.0243 on the blue side, and you see at equilibrium that has been diminished. And you see this also has been diminished, okay? But you also notice that product has been formed, the carbon dioxide and the hydrogen gas. And the K value, if you were to calculate this out, is 0.640. Whereas here you only have the product, you only have this, okay? And then as time passes, you end up forming the reactant. And if you were to take if you were to plug the values in, your K is also 0.640. So no matter whether you started from having a bunch of reactant or a bunch of product or somewhere in between, your K value is always going to be the same, which is 0.640. Okay, now here we can kind of think about what's going on. When Q is less than K, so in this scenario, you see that Q is 0.000 and it's less than 0.640. That's my K over here. Then that means it's going in the forward direction. It's going in this direction, meaning it's trying to form a product. If the Q is bigger than K, so in this case, it was an infinity, is definitely bigger than 0.640. That's this scenario here. And you'll notice that it eventually goes into this point and it's going into the reverse direction. So it's all the product is forming into here. But when the Q and K are equal to each other, then that means we're at equilibrium. So let me give you a scenario for here. So which one for this one, okay? For the very last mixture, number 3. Which direction is it going? Okay, you notice that the Q value is less than the K value. That means it's going into the forward direction. So mixture 3 is going into forward direction. Mixture 2 was going into the reverse direction. And then mixture 1 was going into the forward direction. If I have a mixture 4 and that reaction quotient was the same value as equilibrium constant, then it would be it's not a forward or a reverse, it's at equilibrium. Let's do a learning check based on what we have learned so far. So here it says, based on the reaction with equilibrium constant 0.640, so this refers to what we have learned in the previous slide, determine which direction the reaction proceeds as it goes to equilibrium in the 3 of the experiments shown below. Okay, so we're going to take one step at a time. So we'll go ahead and set up the QC. QC is carbon dioxide and hydrogen, and carbon monoxide and H2O. So we'll do experiment 1, and then you can try experiment 2 and 3 on your own. For experiment 1, we're going to go ahead and plug in all of the values. So we have 0.0040, and then I have another 0.0040 all over 0.020, 0.020. I'm putting these parentheses just to help me segment them separately. 0.0040 times 0.0040. Okay, I'm going to press enter, and you're going to divide that by whatever multiplication under, which is 0.020 times 0.020. And that gives me 0.04. 0.040 to keep the sig figs. So that's my Q. So what does that tell me? My QC, therefore, is less than my KC, right? My KC is 0.640, whereas my QC right now is 0.040. So what does that tell me in regards to, was it going in a forward direction, reverse direction, or have we reached equilibrium? We know that it didn't reach equilibrium because the values don't equate to each other. Having the QC less than KC means that it's going into the forward direction. More product should be formed. So it's going to forward direction. So go ahead and try for experiment 2, and then you're going to try for experiment 3 as well. And come back. So here is the key. Let's do the next learning check. The next learning check says, calculate the reaction quotient and determine the direction in which the following reaction proceed to equilibrium. So here it gives you one scenario. You have a 1 liter flask containing 0.05 moles of nitric monoxide. And that and also gives you the moles of chlorine, 0.0155 moles of chlorine, and 0.500 moles of NaCl with it gives you the equilibrium constant. So we want to know what is the reaction quotient at this time, and also is it going to go into a forward or reverse direction. So for part A, we'll do that over here. We know the reaction quotient is going to equal the product NOCl2 to the second power, and we have the reactant, second power NCl2. The thing is, all of the values that go in here, they must be expressed in molarity, not moles, molarity. So we do need to find molarities for every one of these, and it's actually fairly easy. So let's go ahead and find molarity with regarding, oh, I forgot there's a typo here, which is Cl2, that should be gone. Okay, NOCl. NOCl concentration is moles over a liter, and it tells you the moles right here. That's 0.500 moles over 1 liter, and it gives you right here 1.00 liter, which will then equal out to 0.0500 molarity. And how about the concentration for NO? Well, concentration for NO, it gives you 0.0500 moles of nitric monoxide, and then you have 1.00 liters molarity. Okay, and you do the same for oxygen, or not oxygen, chlorine. Okay, and then it's 0.0155 moles over 1 liter. So therefore, this is 0.0155 molarity. So we'll go ahead and plug those into this value, into the reaction quotient. And this would be 0.5 to the second power. And then we have nitric monoxide, which is 0.055. Oh, oops, 0 to the second power. And then you have 0.0155. Okay, a bit of a handful there. So let's go ahead and calculate this out. We have 0.500 to the second power. I'm going to press enter. And then you're going to divide that by all of the values that are inside. So it's going to be a little bit tricky. So we're going to go ahead and double parenthesize. The first parenthesis is 0.0500 to the second power, and close it. And then my next parenthesis is 0.0155. Go ahead and close that parenthesis. I'm going to close it again. And then you get 6,451. So approximately with 3 sig figs, 6.45 times 10 to the third. Okay, and we're going to compare with Kc. So Kc is right here, and that tells me this is 10 to the fourth, which means it's much bigger, right? So Qc is less than Kc. What does that mean? If the Qc is less than Kc, then it is going into the forward direction. All right, so go ahead and try part B. And in the next slide, there's actually part C. Go ahead and do those and try and come back and check your answers. So for part B, you'll notice that there is only reactant. Okay, there's only reactant present, and that's the only information it's given. So even if you try to solve for molarity, it really doesn't matter because I don't have any products. So my QC here is going to be 0. And so therefore, because QC is 0, QC is less than Kc. So therefore, this is also going into the forward direction. This is for part C. I do want to cover a little bit regarding part C. So in the beginning, you'll notice that it's not giving you the value of each of the reactant and product in moles, but it's giving you two in grams. So you will have to change it into moles by utilizing molar mass. Then divide it by the liters to get your moles over liter, giving you molarity. So that's what I did for NH3, N2, and H2. I took all of the molarity values and plugged it into the reaction quotient and it got 0.23 molarity. Notice that all of these are in response to the significant figure of the grams, and then so is the QC, or the reaction quotient. In the end, the reaction quotient is greater than Kc, meaning it needs to go into the reverse direction.